Research reveals rare metal could offer revolutionary switch for future quantum devices. Quantum scientists have discovered a rare phenomenon that could hold the key to creating a perfect switch in quantum devices which flips between being an insulator and a superconductor. The research, led by the University of Bristol and published in Science, found these two opposing electronic states exist within purple bronze, a unique one-dimensional metal composed of individual conducting chains of atoms. Tiny changes in the material, for instance, prompted by a small stimulus like heat or light, may trigger an instant transition from an insulating state with zero conductivity to a superconductor with unlimited conductivity, and vice versa. This polarized versatility, known as emergent symmetry, has the potential to offer an ideal on-off switch in future quantum technology developments. Lead author Nigel Hussey, professor of physics at the University of Bristol, said, "It's a really exciting discovery which could provide a perfect switch for quantum devices of tomorrow." The remarkable journey started 13 years ago in my lab when two PhD students, Xiaofeng Xu and Nick Wakeham, measured the magnetoresistance, the change in resistance caused by a magnetic field of purple bronze. In the absence of a magnetic field, the resistance of purple bronze was highly dependent on the direction in which the electrical current was introduced. Its temperature dependence was also rather complicated. Around room temperature, the resistance is metallic, but as the temperature is lowered, this reverses and the material appears to be turning into an insulator. Then, at the lowest temperatures, the resistance plummets again as it transitions into a superconductor. Despite this complexity, surprisingly, the magnetoresistance was found to be extremely simple. It was essentially the same irrespective of the direction in which the current or field was aligned and followed a perfect linear temperature dependence all the way from room temperature down to the superconducting transition temperature. Finding no coherent explanation for this puzzling behavior, the data lay dormant and published unpublished for the next 7 years. A hiatus like this is unusual in quantum research, though the reason for it was not a lack of statistics, Prof. Hussey explained. Follow AID for more fascinating news and updates. Thanks.